So to move on with the proceedings for this evening, I am delighted for this evening's James Clayton Memorial Lecture entitled Racing to the Rescue to introduce Professor Tim Baker and Professor Rebecca Shipley. So a few words about Tim first. Tim is a fellow of the institution, as well as an honorary fellow of the Institution of Engineering Designers. In March 2020, Tim co-led the UCL-Ventura group that manufactured 10,000 breathing devices in response to the COVID-19 pandemic. The designs that have since been licensed free of charge to over 2,000 organizations in more than 100 countries worldwide. As background, Tim graduated from UCL, manufacturing engineering with a PhD. Sorry, mechanical engineering, I beg your pardon, with a PhD. Then Tim moved to work with the motorsport industry for over 20 years. Starting with Formula One, he saw his career evolve from engine design to engine development. And after a stint working with Ford World Rally Team, he was the founding member of the Advanced Engineering Research Team. So that during this time, his team created engines that won races and championships at global level, notably class wins at the 24-hour racing at Le Mans. Since 2004, Tim has run a design consultancy company that has helped clients in disparate sectors to turn concepts into reality. Tim returned to UCL to share his practical engineering experience and his experience of prototype design and manufacture in particular. Under his leadership, the department has opened a new student workshop, IMechE space, in central London, which is dedicated to teaching hands-on engineering and industry collaboration. Tim's close links with Formula One, as I've mentioned, led to the partnership with the Mercedes AMG HPP for the UCL-Ventura project that I've already mentioned. In October 2020, Tim was awarded an MBE for his services to healthcare in the UK and abroad during the COVID-19 pandemic. And then in the year after, in 2021, we as an institution recognized his work in response to the COVID-19 pandemic with awarding him with the James Clayton Prize. Tim, welcome this evening, and we look forward to hearing your talk, together with Professor Rebecca Shipley. So Rebecca is a fellow of the IET, and also an invited fellow of the Royal Society for Arts, Manufactures and Commerce. Since graduating from the University of Oxford with degrees in applied mathematics, she has established a multidisciplinary research program at UCL around mathematics and computational modeling in relation to medicine and biology. She works in diverse areas such as nervous system repair, cancer, and psychology of critically ill patients, with a focus on better understanding the biology of diseases, as well as also designing interventions which will change patient outcomes. Becky has been rather a director of the UCL Institute of Healthcare Engineering since 2018. She is co-director of the Hospital Biomedical Research Centre and a non-executive director also of the Royal National Orthopaedic Hospital HNC Trust. She has been recognised for her services with several prestigious prizes, for example, the Rose Trees Trust Interdisciplinary Prize in 2016, as well as the Women's Engineering Society Top 50 Women in Engineering in 2021. Also, from March 2020, Becky was involved in co-leading the UCL-Ventura program together with Tim. In summer 2021, Becky was awarded the OBE for services to the pandemic, and we congratulate her on that, and very much look forward to her contribution to the lecture this evening as well. So if I could invite both Tim and Rebecca to the lectern, and very much enjoy listening to your talk this evening. Maybe a few words of housekeeping with regard to the live stream. So the live stream is taking place at the moment. Those who are actually listening in, you should have access, I think, to the presentation slides, although you can see them in the background on the video. And then during the question and answer session later, we will be taking some online questions. So now's your time to prepare what questions you may wish to pose to Tim and Becky from the talk. So, Tim, Becky. Thank you very much.
Thanks to Alice and Phil for the welcome. It's nice to see everybody here. So we're going to give you a snapshot of what happened back in March 2020 and how we managed to pull together a team to create breathing devices for the COVID pandemic.
Brilliant. Good evening, everyone. It's a real pleasure to be here. So this is a bit of a summary of what we're going to tell you about. Tim and I are both engineers, but our response really brought together a big team across a whole range of sectors. So rather than kind of purely focus on the engineering contributions, we want to really get across the full story of how the work that we did came together and the impact that it had. So we're going to talk through really the chronology of what happened. So we came together right at the beginning of the pandemic, and those first kind of few days, well, hours, days, weeks, were really exciting and moved at pace. So we're going to try and convey kind of what we were up to, how things evolved, and then give you a feel for the devices that we developed, why we took the path that we did, what routes we had to get through to deliver them as new medical devices into the National Health Service, and then following on from that, some of the global impact that we've sought to further develop and deliver.
That's it. And also, it's not just about the Ventura. We'll sort of cover some of the other devices that we got through approval, and also how we set up all of the logistics to get everything out into the NHS and further afield. Okay, so let's start back to the beginning. Get you back into the mindset of the middle of March in 2020, and we're going to start Monday the 16th of March.
I think I'm starting. So apologies to take you back, but if you think back to that time, the UK was essentially in crisis. So COVID had been picked up, was spreading in China, had moved over and spread over to mainland Europe. And these were the kind of headlines that we were facing. It was pretty scary, to be honest. The UK was particularly vulnerable. So as you can see on the graph over on the right there, we had one of the lowest numbers of ICU beds per capita in Europe and indeed in the developed world. And so we were at risk of, kind of healthcare system collapse, really. At the time, there was a lot of modelling going on, as you'll remember, about the number of patients that might be infected and might need hospitalisation and access to ICU resources. So at the time, I think there was a modelled need for 30 to 40,000 mechanical ventilators, which are the devices that are needed to support patients in the most severe of respiratory distress. At the time, the UK had a small number of thousands of mechanical ventilators. So there was potentially a huge crisis that we were going to face, and that was a multifaceted crisis. It was a crisis of, do we have enough equipment to be able to support the number of people that might need it? But actually, much more than that, even if we could solve the equipment crisis, how are we going to have enough trained healthcare workers to actually use those devices and to be able to treat patients?
Good. I'm a bit nervous because Becky's got the clicker. So I'm worried
I'm in control.
I'm worried if I'm going to have to start saying next slide, please, but we'll try and avoid that one. So much like everyone, if we just take it back a day on the Sunday, I was at home and I happened to walk through, the TV was on, and I saw Boris Johnson announcing the ventilator challenge. And I kind of looked at the telly and, companies being mentioned. And I kind of thought, I didn't know anything about ventilators. I didn't know anything about the healthcare side of it. But I kind of thought that it's quite arrogant to suddenly think you can sort of go from standing start to making ventilators, which in my head would obviously be fairly complex pieces of equipment. And I kind of thought with my motorsport background, what you need to do is you need to get into the motorsport sector where you've got very high precision, high quality, very quick turnaround of manufacturing. Thinking, if I was going to do this, I'd get into that sort of situation and look towards those companies. Not for one instant thinking that within 48 hours I would actually be in that situation with Becky starting to look at that. So just a casual look at the telly as I wandered through, and probably nothing more than that, really. Next slide, please. What had happened at that stage, we'd advised all the students that it was time to head for home. It was very strange. The whole place was just completely deserted very quickly. So this is our lovely engineering centre that we'd set up in King's Cross, and this was going to become the home. You'll see in a few slides' time, this becomes the home of the Ventura project. Do it. Yeah, thank you. We'd seen all the headlines. I stopped home on the way home that day and went to the supermarket. And I kind of thought, is it all just hype? Is it all panic? I came to a meeting on Friday at the IMechE, and a couple of the people I was with saying, don't worry, it's all a big fuss. 2 weeks' time, you see it'll all have blown over and we'll be back to normal. So I stopped off at the supermarket, and sure enough, the shelves were emptying, and it was kind of like it was appearing on the news.
And actually, at that time, I was due to be flying to India. So up until a few days beforehand, we had a planned UCL trip from the healthcare engineering teams to visit the All India Institute of Medical Sciences in New Delhi. And up to a couple of days beforehand, we were resolute. We were going. We were like, it'll be fine. We'll fly out there. And then they shut the airspace, so we couldn't go, which I think was one of those closing door moments, because had we actually gone out a couple of days previous, we would have been stuck there for months. But we didn't. So I run the Institute of Healthcare Engineering at UCL, which is essentially all about interfacing our engineers with our medical and clinical science community to develop medical technologies. So obviously the ventilator challenge and the situation that we're in with COVID was of massive interest. So on the Sunday, I was sat in the pub having a pub lunch with my family, and a colleague rang me because she'd been contacted by DFID, as was at the time, to run a design sprint to try and repurpose open source designs for mechanical ventilators that were used in low and middle income countries to see if we could understand whether they were appropriate for COVID and potentially coordinate manufacture. So we started running those challenges online, bringing together intensivists and medics that we had access through UCL with engineers, and of course it was much wider than UCL at the time. I worked very closely with some of the intensive care teams at UCLH who got in touch about a specific set of projects, which obviously we're about to tell you about. And it was very clear to me that we could do the engineering, we could do the kind of understanding of the healthcare piece because of the collaborations that we had in place, and we needed the manufacture piece. And our department at UCL is quite diverse, so Tim and I are in the same department. I obviously knew about Tim's background, so I sent him an email, and now Tim is renowned for not answering emails. And this made me chuckle when I found it the other day, because he says he saw my email. Obviously, he didn't reply to it, but he did send me a Facebook message about 10:15 that evening. I remember I was sat in my kitchen at home. It came in. He was like, should we have a chat? So I gave him a ring, and the rest is history. Fortunately, he at least read my email on that occasion. So there we go.
So up to that point, I'd been, it started with a corridor conversation at work. Somebody looked like a 3D printed sort of skeleton for a PPE mask, and one thing led to another. So I said, I could probably help with some manufacture on that. But by that evening, Becky and I had started talking. So I came in the following day, and it was incredible how quickly London had, we've seen many pictures like this now, but at the time to see the tube at Liverpool Street just absolutely deserted. When I came in that day, I'd said to my wife that, I don't know what time I'm going to be home, meaning that day, but it was actually 5 weeks before I went home again. So came into work on not an ordinary Tuesday, but came into work as sort of normal as it was, and then just, stayed in London until we'd finished what we were what we're going to tell you about.
We did eventually get him fresh clothes. That was a relief.
That's going to, yeah.
So this is an opportune moment to introduce Mervyn Singer. So Mervyn is a very close colleague. He's a brilliant man and very close friend now. He is a professor of intensive care medicine at UCL and is one of the senior consultants in the intensive care unit at University College Hospital. Now, I already worked with Mervyn through various projects that I run at UCL. And as someone put it at the time, Mervyn's not afraid to take a contrary position. So he got in touch and basically had been talking to China and Italy about their experiences of treating COVID patients and essentially laid down the gauntlet that we were thinking about the wrong problem by thinking about mechanical ventilators. And, you know, in addition to bolstering the UK capacity in that space, we needed to be thinking about how to try keep people off ventilators, because even if we could make tens of thousands of ventilators, we didn't have the trained healthcare staff that would be able to support people on them. He made a very strong argument, and I rang Tim and said we were going to meet him that day.
Yeah, it's also, we've been asked a lot about how we sort of pulled everything together. And I think in simple terms, when they were looking at ventilators, it was kind of like how many cases predicted, how many ventilators we got, one minus the other equals how many ventilators we need. But we were coming at it from a slightly different, well, a very different approach, as in, you know, there's a problem to solve. What is the best solution to that problem? So we got together, the Houseman room, which is kind of like the staff room at UCL. And we were with Mervyn, there was me, there was Becky, there was Hugh Montgomery, who's another intensivist. And I'd say it's one of there were two really scary meetings during this project, and this was the first of them. To hear that the modelling was showing just how many cases there were going to be, and that they were going to be calling in the army to be guarding the hospitals, and they just had this huge shortage of devices. And what could we do to help, in simple terms? So the way I described it was, you probably don't need all of your touch screens and the electronics, because we're not going to have time to be able to manufacture those, and the components probably aren't going to be around. So obviously with my sort of automotive background, I suggested we need to go carburetors rather than fuel injection, and go a little bit old school. So that kind of like started a conversation. Well, we probably got something that we used to use 15 or 20 years ago. So maybe we could go and dig something out, have a look at that and see whether it's something that you could replicate in quantity and at speed. Obviously, as it turned out, the modelling, what happened was everybody pretty much listened to the instructions for the lockdown and stayed at home. So that really helped with controlling the surge. I mean, obviously it was very bad as it was, but their predictions were it was going to be far, far worse. So for us, by this stage, stuck in London, it was very scary to know that we were going in and out of the hospital that could possibly be, guarded by the army. So let's explain what it is that we developed and sort of the way that it works, and then we'll explain the actual device and how we did that.
So you mentioned a bit about respiratory support and COVID. So essentially, if someone has COVID and is hospitalised, they need respiratory support. They need help to get as much oxygen as possible into their lungs. So we ended up making continuous positive airway pressure devices, or CPAP devices. So this is the abbreviation that you'll hear very often. And essentially, what CPAP devices do is that they kind of inflate the lungs via positive pressure. So they kind of splint open the lung bases so that you can get more oxygen into your lungs than you would do if you were just using a standard face mask. And they're very simple. This is a little caricature of how they work. And essentially, you have a flow generator that's connected to a patient via a face mask and that's plugged into the hospital oxygen supply system. Now, CPAP wasn't new. So CPAP is commonly used to treat patients with respiratory distress and also in home settings under slightly different guises. For example, for patients with sleep apnea, they've been around for hundreds of years, so they weren't new. It's not a new method of treating patients. It was just a bit of an unknown for treating COVID patients. And there was a huge amount of controversy at the time. There were a lot of concerns about CPAP, and that was really the setting that we were coming from. So at the time, there was the ventilator challenge. The common dogma was that if patients needed more than face mask oxygen, that you should mechanically ventilate them, and that was the background that was being used around the world. The concerns were multifaceted. First of all, because CPAP's delivering oxygen at high pressure, it can aerosolize the droplets, so there was a concern about what that meant in terms of spreading the virus. And secondly, CPAP can be very oxygen hungry, and there were real concerns about what that meant in terms of hospital oxygen supplies. But you can see here, this is a newspaper article from the time, and this is a picture of a hospital in Italy, and these patients are all sat there on CPAP. So we learned very quickly that that was part of the response that other countries were using.
Okay, so if you look at this graph, we're sort of, by this stage, just about halfway through, perhaps just between those two dotted lines. Nice bit of data, we're engineers, we can follow those sorts of trends. So we're in this situation, we know what's coming, but we seem to have, we're watching a slow motion car crash happening. We're seeing this data coming from Italy, and yet there doesn't seem to be an adequate response. So that's why, again, ventilator challenge is happening. Ventilation is the preferred treatment, and yet we're starting to look at doing something contrary to the recommended route of treatment. So that's where we were at that point.
And the reason why we were doing it was because Mervyn had this incredible international network. So he knew the intensivist who was in charge of the response in Wuhan, and he had a whole collection of intensivist colleagues across the Lombardy region in Italy. And he was reaching out to them and talking to them and understanding what their experiences were. So at the time, their hospitals essentially started collapsing when they were mechanically ventilating all the patients that came in. And so they started using CPAP. Their experience was keeping around 50% of patients away from needing mechanical ventilation, which is good for the patient because mechanical ventilation's, it's highly invasive, as the name would suggest. Patients are often sedated for weeks at a time, and they need all sorts of extra support, cardiovascular support, renal support, etc. CPAP patients are awake. They can eat, they can drink, they can communicate, and usually the length of stay in hospital and on intensive care is much shorter. On top of that, it also alleviates, obviously, the burden on mechanical ventilators and highly trained staff in the hospital. So there was an opportunity to kind of optimize healthcare resource and improve patient outcomes. But obviously, we would need a very simple design. At the time, we couldn't just import loads of extra CPAP devices because obviously all countries were stockpiling their resources for themselves. So we needed a simple design that would be easy to train healthcare workers to use, and that could be manufactured at speed in a pandemic where all global supply chains had collapsed. So it wasn't a small ask, but nonetheless, we decided to go for it. And this just gives you a feel for some of the background at the time and how controversial actually CPAP was. So this is the American Society of Anesthesiologists against CPAP at the time. A few other examples: Australia and New Zealand, not recommended. The list goes on. And as I said, some of the big concerns were really around spreading the disease via the aerosolized droplets. And in fact, I remember being on an international call once with the WHO where someone from Harvard Medical School said that I was proposing that we were going to weaponize COVID for the developing world. It was that controversial a position at that point in time. But nonetheless, from Mervyn, talking to all of these colleagues in Italy, so this is an Italy example, they introduced CPAP into their care pathway, and anecdotal evidence, collecting emails, sat writing emails at midnight in the research offices at UCLH. We managed to collect a lot of data about experiences in other countries, which, to be honest, the government weren't doing this in the same way at this time. We collated the data and we made the case. And ultimately, the NHS care pathway changed to include CPAP on the escalation pathway after face mask oxygen, and that happened on the 26th of March. So we'll come to the 26th of March anon, but I think it ended up being the right position to take.
Yeah, we're getting ahead of ourselves a little bit. Meanwhile, I was busily starting to look at the engineering. It's amazing. When we stopped later on and started putting some presentations together and talking to people, there was so much going on behind the scenes that I wasn't aware of. I kind of knew that CPAP wasn't the chosen route, but I didn't realize that we were actually going to change the care pathway of the NHS to get our device included. So, as I mentioned, we were going to get an example of a device that we could possibly copy. You may say, well, weren't these devices out there? Obviously, technology's moved on, so all has data loggers and screens and so on. But just to put it in context, at that point, Mervyn was saying that in UCLH at that point, I think they had something like 112 ventilators, and they had
12 CPAPs.
12 CPAPs. So there was a complete imbalance in numbers if they were going to go down the CPAP route. So on the left is the display cabinet from one of their sort of museums that they have at the hospital, and they're highlighted. If you just hit the clicker, there you go. That is the CPAP that was taken out of the display cabinet, and this is the one that we got back to our engineering centre in King's Cross to start looking at how we could reverse engineer it. Now, this meeting happened. We were waiting, what's this device going to look like? We had no idea, and it arrived in a carrier bag while we were waiting at Patisserie Valerie on Torrington Place. And we opened the carrier bag, and it's kind of like, we can do this. This is going to be something that we can actually get to grips with, because it's just a very simple mechanical device. So this is the Wednesday afternoon. In the centre there, this is Ben Hodgkinson. So at the time, he was working for Mercedes-AMG HPP. In simple terms, they make the power unit for the Mercedes Formula One team and their customer teams. I've known Ben for many, many years. I sponsored him as a student when he was at UCL, and then gave him his first and second jobs in motorsport before he's always a brilliant engineer, and then he was always going to head for Formula One. And then he rose through the ranks to head of mechanical engineering at the Mercedes HPP team. He comes back to UCL. I can see we've got some of our students here. I don't know if you had the pleasure of being grilled by Ben during any of your assessments. There's a few nodding heads there. So he comes and works quite closely with the university. So at that point, the Australian Grand Prix had been cancelled. All the engines had been sealed, so they couldn't be touched. So I kind of thought, well, Ben's going to be stuck because no more developments, engines sealed. So I sort of said, do you reckon you could come down and perhaps have a look, see what we're up to, have a look at the design? Without any question, he just hopped in the car, came down to London. And so the first thing we did is take this museum piece and put a bandsaw through it, because we didn't realise it was someone's cherished piece of an antique. And we started measuring it and seeing what we could do to recreate it. It was going at an incredible pace at that point. You may wonder, why didn't you go to the manufacturer to see if we could get the manufacturing details? Well, we tried as hard as we could. And I think it probably turns out that we got to within, say, 2 desks of the person that we needed to talk to. We've spoken to them since. We were that close to finding the designs. And as it turned out, that the patent on this had run out 6 months previously.
Yeah, 6 months.
So we had a team that were checking out the patent situation and worked out that, well, great, we can just get on with copying this actual device.
And one of the real benefits of this device was that it had obviously been previously CE marked, so it would meet regulatory standards. And actually, if you went into the hospitals and spoke to nurses on the wards, they actually remembered it from using it about 10 years ago. So there was a real hope that by delivering these devices, a lot of people would remember how to use them. So this is one of the first team photos. It was that same day. This is at the IMechE space. So you can see Tim. We had a bunch of students and technicians involved. There's Ben in the middle. This is Dave Brearley, who was one of the clinical leads. He's another consultant in the intensive care unit at UCLH. And there's myself.
Yeah, hit a click. Thank you. So on the right is Chris Buckingham. So this is how we sort of put the team together. You never know where the inspiration is going to come from. So having left home, my wife messaged me and said, oh, there was somebody on our local news who says that they're trying to get in contact with the Cabinet Office in number 10 because they can help. They're a medical supplier, but they just cannot get through to, they can't get any sense. No one's answering any emails. It just seems to be a very chaotic situation. So that's the screenshot that she sent me on my phone. So I did a quick bit of Googling, found this person, rang them up, sort of said, oh, we're trying to do something with CPAP. Oh, yeah, I seem to remember that device. You wouldn't come to London, would you? Yeah, why not? So hopped in a car and came straight down to join us on the day. Chris was just the most incredible source of information, because he's obviously involved in the manufacture of respiratory devices. So when we were sort of, Chris, what do you think this material is? Oh yeah, we know what that is. That's fine. That's probably what you need to use for that. And he knew sort of, the suppliers, who they would be. he was absolutely brilliant. So for the next sort of 10 days or so, we kept in really close contact with him. He helped on the technical side. He knew where the threats were coming from, because we did have threats coming our way, surprisingly. And he just, it was a great source of information for everything that we were doing. So this is late into the night on the first day of designing. Ben's called some of his other design team. Obviously, they've got a huge team over at Brixworth, where they're based. But again, others of them, just no questions asked. Either, I think some of them came down on the train, jumped in the car, and we just set to. So you can see by that stage, we've got all of the inspection equipment, and we're just measuring up, and we're starting to create the 3D CAD models to reverse engineer. Just a nice little aside, if you look, I think this is like the early hours of the morning. We've got some beers open on the desk. That's Corona beer. Do you remember it was the coronavirus? Shelves have been stripped, but right there, you could have as much Corona beer as you wanted.
No one was buying it.
No one was buying it. So, we just carried on and on until sort of, I don't know, it's about 5 a.m. and we decided perhaps we should go and get some sleep. It would be a good idea to try. Again, motorsport, you do tend to have all-nighters every so often, so we're used to that sort of territory. But we went to the hotel. I mean, our brains were spinning. We met for breakfast and just came back again. I don't think any of us had any sleep that night. Over to you.
Over to me.
Thursday the 19th.
Thursday, right, the next day. So this was the point now, so we were a few days in, where it became real to me, I think, for the first time, that we could actually do this end to end. We still were kind of bonkers, to be honest. But Mercedes were on board. We had the engineering capability. It was a simple device. We had the healthcare need. So we had a shot at doing something that was meaningful. So one of the first things that we did that morning was invited these two chaps up to the design unit, to the MEC space, to come and see what we're up to. So this is Brian Williams. He's head of the Biomedical Research Centre at University College London Hospital, and this is Nick McNally, his sidekick. So they came up. So Brian is a practicing clinician. He was, front of house in the A&E at UCLH when patients were flooding in the door. So invaluable expertise around what was actually needed in terms of these devices and treating patients. I prepped Tim. I was like, right, someone high up in the hospital's coming up. I'm going to introduce you to them. We have to impress them and make it really clear what we're up to. In they walk, and Tim stood there with his flies open, wearing clothes that he hasn't washed for about 5 days. So nonetheless, they still backed us, thankfully. So
we're trying to convince everybody, and that also includes at cabinet office level. So again, behind the scenes, there was quite a lot of sort of political movement to try and help with that. So David Lomas, who's our Vice Provost for Health at UCL, he was very busy trying to get the momentum there's so many groups out there to get us listened to, that we got something, okay, not a ventilator, but it's something that would help. So we got to the point on the Thursday where we had a very brief window. It's something like a 2-minute window where there would be a representative at number 10 who would look at what was going on and would make a decision whether they were going to back us to take it any further. So Ben and design team were very busy trying to get together a nice one slide of what we'd got. And you can see what the point we got to. I have a big thing about first impressions. You only get a single chance to make a first impression. And they were busy trying to get the logos on there onto this slide. Meanwhile, Becky's going, come on. We've got this 2-minute window. We've got to get there. And then suddenly Becky's on a phone. Well, Becky's kind of like got phones and laptops on an ordinary working day, but even more so at that stage. And suddenly it's like, we're on, number 10 are on. So suddenly Becky's like, come on, I need the picture now. And I think she actually took a screenshot.
I took a photo on my phone.
Yeah. Just took a photo on the phone. And then that was kind of like WhatsApp, because I think that was the way the number 10 communicated in those days. and then the discussion started as to whether they were going to support the project that we were looking at. And to the next one. So we were starting to get the backing for what we were doing. Meantime, I was pushing my luck, so I said to Ben, do you reckon you could get a sabbatical for a couple of weeks to perhaps lead the design that we're doing? So he went back to Andy Cowell, who is pretty much in the center of that picture, and asked Andy if could I get a sabbatical? Can I go and help? Is there something we can do? Is there more that we can do to support this project? And Andy sent back a message which he said, do not hesitate to call upon the might of what we can do. So this is the mental picture I then had in my head. Wow, we've got half of a Formula One team to play with now. Now we're really in business. That's unlocked the high precision manufacturing that I was thinking about on the Sunday. So that meant that we were now in a position where we've got a device, we've got the designs, now we're really in a place that we can start manufacturing it at pace. So what is it that we actually did?
Brilliant. So you've seen this picture at the back here. This is the Philips Respironics whisper flow device, which is a CPAP device, a flow generator that we found in the Anaesthesia Museum at University College Hospital. Essentially, what we decided to do was start by doing an exact replica of that device because, as we said before, it's a simple device, no embedded electronics. Previously, CE marks had a clinical user evidence base, and we had a hope then of getting it through the medical regulator quickly. So the first thing we did was to generate an exact replica. This is the UCL-Ventura Mark I. This is the device here. And then we're going to tell you the kind of design story in a second. But I mentioned at the beginning that one of the big fears, which was a very valid fear, was that our hospital oxygen supplies would collapse because of the pure volume of demand that was going to be put on them by the patients, number of patients that were coming through. So we needed to do everything we could to minimize how much oxygen this device needed to provide CPAP to a patient. So we did a lot of design work and optimization of the breathing circuits, which are the bits that connect the tubing, the masks, etc., that connect the device to the patient, and managed to significantly reduce the oxygen utilization. So this was the Mark II device. We're going to tell you more about this story in a second. And this was the device that essentially went forward for mass manufacture and rollout into the National Health Service.
Hold it right there. I just mentioned a few things about that just before we progress. So how does the device work? It blends oxygen with air, and it's a very simple Ventura device. So it has a high-pressure jet of oxygen through the throat of the Venturi, and then you can see there's like a turret sticking up in the middle of the blue CPAP there, and that's an air entrainment port. So the Venturi draws the air in, and then just by controlling the amount you've just got simple valves, so you can control either how much flow you have or what percentage of oxygen blend you're going to have. So you can go from basically atmospheric air pretty much right the way through to 100% pure oxygen if you need. Okay, yeah. That's good. Right. So Saturday the 21st, as mentioned, we'd all hopped in cars and headed to London with no thought of taking spare clothes with us. If you leave engineers to look after themselves, it gets pretty messy fairly quickly. So I've just mentioned that it was a Venturi device. Now, we took one of the younger members of the team and said, can you head out to King's Cross, St Pancras? There may still be something open. Can you at least go and see if you can find us some, spare underwear, some socks, anything just to make life a little bit more pleasant. And this is what they came back with. So these are actually pajama tops. We had a choice of I think there's an M&S that was open. We had a choice of either full-on dress shirts or these. So they chose these. And this is in the Royal National Hotel in the middle of Bloomsbury, great big hotel. And we're there at breakfast, put our nice new T-shirts on. There's a few tourists who haven't managed to catch their flight home in the restaurant having breakfast with us. We just look like the most badly timed stag do in all of time. So if you look carefully, can you see? So the name is Ventura. So this is San Buenaventura on the T-shirt, and this is where the name came from. We had a lot of resistance from our powers that be to call it Ventura, but we were kind of like, there's no bargaining on this. The device is going to be called Ventura, or else we're all going home, and that's where the name came from. Brilliant.
So at this point, we've gone from a standing start. The team have reverse engineered the device, and Mercedes have made the first few prototypes of them. So on the Sunday, from first meeting on the Tuesday evening, Mercedes representatives turned up on the Wednesday. On the Sunday, we're ready to go into the hospital with some prototypes and see if they were up to it, essentially. Tim mentioned scary meetings as we went through the project, so I think this is probably the second scary meeting that Tim was referring to. So this was the point where I think in terms of us communicating with the NHS kind of management, that it became very real that we would be able to provide these devices in volume. So this was where it kind of flipped from being an idea from a crazy bunch of engineers bunkered up in King's Cross somewhere to something that might turn into reality. And this is where all of the kind of NHS response, hospital oxygen pressures, etc., came into play. So this was a meeting on that Sunday. To give you kind of context of us going against the grain of the dogma at the time, I was rung that morning by a high-up representative to essentially warn me off working on this project, to say that they were very worried that I was going to risk my reputation as an engineer by picking the wrong problem to tackle working with Mercedes. I didn't really think I had much of a reputation to lose, to be honest, so it didn't really bother me. So we cracked on. But we then walked into the hospital with the devices and joined this meeting, which we'd instigated, where essentially there were real concerns about hospital oxygen supplies. So I mentioned before that CPAP is traditionally very oxygen hungry. And we were launched into very serious conversations about what would happen in that kind of scenario and what we could do to mitigate it. I think it's worth saying we talk about a complex background to this project and lots of competing politics, but the NHS response was absolutely formidable. So at this time, University College London Hospital had gone from having about 30 ICU beds to immediately repurposing most of the hospital and more than doubling their capacity. The people working on the ground were utterly formidable. So this is when the Mercedes team turned up. So there's Andy Cowell on the left there. You can see he must have had a tough night because he's still having a snooze. There's Ben in the middle. So they turned up with the devices. These are the first few prototypes. I mentioned Dave Burley before. We kind of got him to run out of the hospital in his scrubs to take a photo. And Tim, so the context here was we were going into the hospital. COVID patients were streaming through the doors. We didn't really know what was going on in terms of infection control, or, it was a brave new world at the time. So in a sense, it was quite scary, but I don't think we really thought about, or I didn't think about it that much. We just cracked on. So at that time, Ben was actually COVID positive, and we didn't even realize. So I remember him saying he had a bit of a headache.
Yeah.
His daughter had been at the party in Camden not long before, and then basically all of the parents got sick. He'd just driven down in a car with Andy all the way, said he was feeling a bit under the weather, so Dave just gave him some paracetamol in the hospital and we cracked on. I think we were very lucky that the rest of us didn't get sick because we weren't wearing masks and we were in really close proximity to each other. And we didn't really have a resilience plan, so if we'd all got sick, there was no backup.
We just kind of thought we were just going to keep going till we dropped. That's kind of like how it felt at the time. What we were doing, though, is we were all living in isolation by that point. The threat from UCL was to put us in a student hall of residence, which we were like, maybe not. So we ended up with an apartment each. We were going to try and get a townhouse. We thought it was all about, just the separation and each having en suite and that kind of thing. Again, no masks and social distancing as such, but we were very careful not to be touching each other, which is why it was all elbow bumps and that sort of thing. But so we lived in our own bubble in the evenings and then came back to IMechE space for doing the engineering each day. So the first CPAP device, there it is. You'll notice that there's part of the tubing, so that's the patient circuit or the breathing circuit as it's known. I'd sort of started inquiring about where those components came from, and then we very quickly learned that there was a huge shortage of everything. So all of the piping, the masks, the filters. You're going to hear a story about oxygen sensors as well a little bit later on. So we turned up and we were going to do testing. We'd benchmarked it. It matched the whisper flow, perfectly. So we just kind of thought, that's it, job done. Going to hand it over. Go and make lots of them. Thanks very much. Pat on the back. All very, very straightforward.
So we plugged them in. We plugged them into the oxygen supply ports in the hospital. Merv and Dave kind of pulled together a random breathing circuit from the cupboards, put it all together, put it on, and essentially they couldn't really breathe. There was it was a really heavy work of breathing. There was a lot of resistance to breathing. So they kind of just looked at it and said it's not working. Now, we knew, obviously, that the actual flow generator device, it had been bench tested extensively, so we knew that it matched exactly the characteristics of the whisper flow device, so it must be something else. So, we were expecting, as Tim said, this mic drop moment, done, off we go, make loads of them, get regulatory approval sorted. And it could have ended there. I think if we hadn't had this really close iterative collaboration where we were in the hospital and talking to people and we were all there problem solving, the response would have been, it's not working, move on to the next thing. But of course, it was just another problem to solve.
That's it. And I think that's where what we did really worked. We had this sort of golden triangle. We had the mechanical engineering, we had the hospital and the intensivists, and then we had the industry collaboration for the manufacture, and that's where it really came together. And I think if we just handed the device over at the door and then Mervyn and Dave had come in and tested it on their own, they might have thought, well, it doesn't work, and come back and said, sorry, it doesn't work. All right, well, we'll go and try something else. Dave was kind of like, when he was breathing on it, he was kind of like, it's not how I remember. There's something that's not the same. It's really such hard work. So we then sort of jumped into action, and it's right, okay, let's engineer what's going on. So very quickly, we went and found just a clear piece of tube. There's lots of that in a hospital ward, and we made a simple water manometer, because these work at a pressure of 10 centimeters of water. Brilliant. Well, let's make a simple U-tube manometer, and let's measure how many centimeters of water, just by eye, what we think we're getting. So, I don't know, just if you gauge it, something like that. We were getting far, far more. We could just see visually. We went and found the ruler in the end and started measuring. So then we started putting T-pieces on, and we doubled the flow area, and we started dropping the pressure. So we started homing in on the fact that a lot of the components, they just didn't have the flow area for a device like this. Technology's moved on. So a simple way to describe it is now you have, £30,000 worth of complicated device to compensate for a few pounds of cheap plastic, because they're not very good flow devices. So we needed to find a solution, and this is where, again, a lot of the work came in. We spent hours and hours and hours. We flow tested every single filter and T-piece and mask and so on and so forth. And you'll see as the story develops how we then were able to reduce the oxygen consumption, but also the pressure in the system, so it became more bearable for the patient that was actually using the device.
So that takes us into week 2. So week 2 was when the oxygen question really came into play. So will hospital oxygen supplies collapse? So I've put at the top here some of the data on how much oxygen different respiratory support devices use. So, if you go into hospital, your kind of first port of call is to give someone face mask oxygen. That uses up about 15 litres per minute of oxygen. So this is a low amount in the grand scheme of things. But you can imagine you have hundreds of patients in one hospital at one time on this, you start getting loaded up. A mechanical ventilator, which is the most extreme version of respiratory support, uses up to about 20 litres per minute of oxygen. So again, relatively low in the grand scheme of things. And then in between those two, in terms of the kind of escalation pathway, you've got high flow nasal oxygen and high flow CPAP devices, which can use up over 100 litres per minute. So of course, if you suddenly have lots of devices using that much oxygen, the system might collapse. And in fact, that happened in instances. So these are some of the reports of critical incidents that came out. This one was at Watford at the time. Watford was one of our trial centres, and they had 10 of our devices that were being used when this happened, and so the finger kind of pointed at us in terms of whether it was our devices that were leading to this. But of course, there's different ways to tackle this kind of problem. So there were real clinical benefits to using CPAP. So the question then became, how do we minimise how much oxygen they use so that we can then balance the demand within a hospital? This this is some of the team. So we started doing a lot of work to really characterize how much oxygen these devices used, but also what that meant in terms of the pressures and flows within the ward. So this chap here is a chap called Malcolm, who is one of the hospital engineers at UCLH. So we ended up doing essentially experiments on different wards at different levels in the hospital, where we were measuring pressures, putting devices on sequentially, changing the flow rates, and really fully characterizing and measuring what that meant in terms of the hospital systems. But there was a lot of worry. This was one of the really kind of stressful points of the project. A lot of data analysis, a lot of concerns about what this meant in real life, and of course a huge amount of responsibility. So we could do a lot of characterization work. We could fully understand what was happening in UCLH because we had access to the full pipe plans, the hospital engineers, but we were potentially sending these devices out into the whole of the NHS, into settings that we weren't there. We couldn't characterize their local setup, and it might be challenging to communicate with them. So I think we were extremely aware of our responsibility as engineers to fully characterize our system and to be utterly transparent around the data, the bounds on when it was appropriate to use our devices and when it wasn't. So we're going to tell you a bit about the regulatory pathway next, but essentially it kind of worked. So 10 days after our first meeting, we got our first device, so the Mark 1 device was approved by the IMechE, which is the regulator for medical devices in the UK. And they essentially define what's safe and effective to be used in the National Health Service. So we finally, for about 20 minutes, breathed a sigh of relief. That came in, and this is basically the team. We went up onto the roof at the IMechE space and took 20 minutes to have a drink and have 20 minutes of downtime before we carried on.
Our own little partygate.
Our own little partygate.
So moving on to some of the development, testing and regulation. Let's go to the next slide. So again, just to give you an idea of where we're heading. So we had the original device. We then developed the Mark 1, and I'll show you in a moment some of the testing that we did to get towards the Mark 2, which had much better flow characteristics. One of the things that we looked at, you can see that we've got this mushroom over the inlet port, and that helps to really entrain the air. One of the issues that you have is if you go for very high oxygen flow rate, when the patient's breathing out, that creates a back pressure, and that tends to wash the oxygen straight out of the inlet, the air entrainment port. So you start losing oxygen that way. That's where it can become very oxygen hungry, because this thing is just flowing the whole time. So as you're breathing in and then breathing out, there's a continual flow of oxygen the whole time. And what we're going to see is that it wasn't just through the device, but through the pipe work. We went from corrugated pipe to a nice smooth bore that we were able to reduce the resistance and then the amount of oxygen that was being flowed. Through Mercedes, we had all of the tools, all of the toys to play with. So you can see we've got scans of the original device. Despite the fact that we'd taken all the parts, it was very quick for them to scan it to see how it was all assembled. And just a nice little overlay of the actual CAD models that go with it. We had a lot of flow analysis going on at the same time to look at the improvement of the Venturi. And also, we had a flow rig going. If we go on to the next slide, thank you. And then we had a flow rig going. So this is a mannequin that was bought on eBay, a shop mannequin, and that was built to become the flow rig, obviously known as Ace Ventura from that point onwards. Got the T-shirt on there, and you can see at that point we've got I think that's a smooth bore hose, and we've got different filters, and by that stage we picked up on the fact that a particular layout of mask was the one that really helped to reduce the oxygen usage.
Brilliant. So we've given you a bit of a flavour of some of the R&D work, but we wanted to quickly tell you about the regulatory pathway for medical devices. So from a standing start, normally in kind of normal times, it might take a decade, 5 to 10 years, say, to start from a new medical device and get it through development, testing, clinical evaluations, clinical trials, CE marked and out for use. Obviously, we didn't have that amount of time. The IMechE were phenomenal. So we developed a really good relationship with them. I think their response to the pandemic in terms of medical devices was fantastic. So they pivoted all of their usual regulatory processes so that non-CE mark devices could be developed and used because of the urgent need. And they took a very pragmatic approach to doing that. So it was a bit challenging for us because obviously CPAP hadn't been on the kind of agenda when we started, and obviously we hit them up very quickly within a couple of days of the team coming together to say what we were doing. They assembled a rapidly manufactured CPAP system specification, so there was complete transparency about exactly what standards and requirements we needed to meet, and that involved a combination of complete data about the design, all kind of bench testing data. And then the kind of stage on from the engineering piece, if you like, is you needed to do healthy volunteer test data. So that was when healthy volunteers, us and others, sat on the devices and we characterised what was happening. And after that, we did clinical evaluations on COVID patients, first of all in University College Hospital and then at sister hospitals across London. And this kind of developed a dossier that we had to submit to the IMechE for them to assess. We then had to put together a kind of a complete reporting mechanism. So to this day, I'm still reporting to the IMechE on a monthly basis about the number of devices out in the field, if there's any adverse events, equipment failures, etc. So it was a massive undertaking, but as a team, we threw ourselves at it. We were lucky because the IMechE were so open. They had continuous communication, so that by the time we came to submitting our dossier, we knew exactly what standards and requirements we needed to meet. And these are some of the examples. So the Mark 1, our pitch was basically that we could generate an exact replica of a previously CE marked device. So we had to demonstrate it was an exact replica. We had to go back to the whisper flow manual and be able to regenerate all of their testing data. So this gives some examples here of the some of the original test data and our counterparts, even down to things that were weaknesses in the design. So the first piece of the puzzle was the grandfathering. We had to replicate that device down to every single detail. And then based on that, we could then evolve the design, and that was our Mark II device.
Okay, so just before we start showing some of the results from testing, just to give you an indication of the parts we were looking at. See, on the right-hand side, it gives you an idea. That's like one of the boxes we had with all the different hoses that we tested. But top left, those are the PEEP valves. They set the pressure. Really beautiful little bits of engineering. That sets the pressure within the system. And then towards the bottom, that is a mask that we've got, and it has a single inlet and an exit port with nice flutter one-way valves. That was very good at conserving the oxygen. And then as I've mentioned before, the tubes, we honestly looked at different diameters and so on and so forth. We tested absolutely everything. So Becky's going to explain some of the results from those different configurations.
So these are some data that actually ended up being in an NHS briefing document that went out in the next wave. So we've talked a lot about wave 1, but actually oxygen pressure on hospitals was even worse in winter 2020 to 2021. But this gives you a feel. So I hope we've kind of communicated that we wanted to be utterly transparent about exactly the operating parameters for our devices. So in that spirit, we released and made all of this information available. But we did a lot of work, as Tim said, to characterize exactly what happened in terms of oxygen utilization at kind of normal breathing rates versus higher breathing rates that mimicked a COVID patient, but also comparing different components in the system. So you can see here oxygen flow rates that for our kind of end game optimal setup. So this is this end here. But if you changed, for example, the smooth bore tubing to a corrugated tubing, obviously that increases the resistance to flow, and so the oxygen utilization goes up. And similarly, single port masks were bad. So in the second wave in the winter, actually, when we generated all these data and they went out in NHS briefing documents, single port masks were actually withdrawn from the NHS at one point because of the pressure that they were going to be putting on hospital systems, and instead dual port masks were used. Finally, before we move on, this is a comparison of our device versus other devices. So it was very interesting at the time. We were newbies on the scene. We weren't medical manufacturers. And we were obviously pushing a new device into the system. So very rightly, there was a lot of scrutiny as to the performance of our devices, and this oxygen question came up continuously. But of course, there were lots of devices out there that were already being used by established medical manufacturers, but because they'd been manufactured by kind of highly reputable companies, they weren't put under the same scrutiny. And of course, they'd been manufactured for a different problem, a problem where you didn't have a limited oxygen capacity in your hospitals. So this compares our device. So 60% FiO2 is the concentration of oxygen in the air that you're breathing in. So these are kind of standard operating parameters, if you like, for treating a COVID patient. So at a COVID breathing rate, we were using about 30 litres per minute of oxygen, for example. And these are comparisons against kind of other standard devices that were out in the NHS and weren't put under the same scrutiny. So the real risk here was that because people weren't interrogating these other devices, and measuring kind of in situ what they were using up and wasting in terms of oxygen, this is where the kind of real danger of oxygen collapse came in. Week 3.
So let's talk a little bit about the manufacture. At the very end of this presentation, we've got a nice B-roll of video that shows it in more detail, but just a few sort of take-home points from the manufacture itself, obviously all happening at Brixworth. So every single device was bench tested, so it was flow tested to check that it was to specification. By the end of the manufacturing run, on the final day, we made, yeah, we were hard at it. 1,200 were manufactured on the final day, and within that 1 month, we made 10,000 devices and delivered into the supply chain. So what did we actually, obviously we've got the Ventura in the center of the picture. We're going to talk a little bit about oxygen analyzers because that also became a real focal point for what we were doing. And what we did was every single device was delivered with all of the pipe work, all of the breathing circuits, the masks, an oxygen analyzer, so it was all ready to go in a box. The other thing that we did, we'll explain in a moment, that we actually pre-assembled everything because we went into the hospital with all the bits and the instructions to check it out. And this is, when it's kind of relaxed and it's kind of like during a break. And the first thing they do is throw the instructions away, see if that fits onto there. There's 2 critical valves. You've got a high pressure, slightly high pressure as a sort of a pressure relief valve. If you get those mixed up the wrong way round, it means that all you're going to do is just be bleeding the oxygen away from the patient. So we took the decision, we're going to have to make sure that these things are pre-assembled, and so you just get the thing out of the box, plug it into the wall and put it onto the patient. Okay, over to you on this little bit to start with.
Okay, I think we've kind of talked about most of this, but Tim just mentioned what's in the box. So we had the flow generator, which were the new devices that we were making. We had the breathing circuits, which we'd done a huge amount of work to characterize and had this very specific design that we sent out with every kit to minimize oxygen utilization, improve patient comfort. And then we needed all the extra bits. So it was very important for safety, patient safety, that you can monitor the concentration of oxygen that's being inhaled by the patient. And that, of course, meant that we needed oxygen analyzers as well. And, of course, the UK doesn't manufacture oxygen analyzers. They're made in other countries across the world who were stockpiling them for local use. So we hit the same problem again, that we needed now 10,000 oxygen analyzers from scratch.
So on one day of the project, I stopped the whole team and let's go and buy every single oxygen sensor in the UK. So everybody was just on the phone and we phoned round and round. We managed to get about 450. We bought scuba oxygen sensors because there weren't enough medical grade ones around. And then, okay, we've got 450. We only need 9,000 and whatever my maths is, and you're the mathematician. However many others.
Still needed a lot.
Yeah, a lot more. So then, again, automotive background, I started thinking, what about a lambda sensor? That measures oxygen. Obviously, it's a very narrow band that it operates in. And so I got in contact with my old boss. We used to have the engine company. We had a sister company that did all of the engine electronics. And it's like, a bit of a crazy idea, but what do you reckon? Could we repurpose a lambda sensor to turn it into a medical grade oxygen analyzer? I'm just wary of the time as well, but in simple terms, that's what we did. We went and made 10,000 oxygen analyzers out of a lander sensor. So I think we've got something on the next slide that just shows you. Also, we've got these components when we do the drinks reception. If you want to come have a look, you can come and see these components in the flesh. So there you go. It's packaged into a casing. The electronics is just absolutely beautiful, all designed from scratch and made in huge quantity very, very quickly. And so we were able to put one of those in every box that we sent out with the Ventura. And apart from that, we actually did 2 oxygen analyzers. We did 2 Venturas, the Mark 1 and Mark 2. Top right is a very simple pressure manometer. Remember, we made a U-tube manometer in the early stages. We made essentially an electronic version of that because it's quite hard to set the flow. In the good old days, the intensivist would just put his hand under the outlet and feel what flow was coming out. Probably not the best thing with COVID around, but also when you've got a glove on as well, it becomes quite difficult to set the flow rate accurately. So we also made a very simple way of setting the flow. And we mentioned about the twin port mask. The real gold standard is the hood that you'd seen in the pictures from Italy. Again, absolutely no supply of those. So with Avon protection, we also produced a large quantity of CPAP hoods to go with everything else that we did.
So yes, I think in total, our team were responsible for 6 brand new medical devices that were fast-tracked through the IMechE and were approved, mass manufactured, and went out into the NHS.
So let's give you,
to logistics.
Yeah, let's go through a very quick snapshot of the logistics. Naively, we kind of thought we're going to make 10,000 of these. That's fairly straightforward. First thing we did was order some boxes, and they turned up, and it's like, we've got a bit of a problem here. We can't even get the boxes in the building. So I got into I've got, Andy Cowell described it, I have a very good black book of contacts. So I got into my network, and we spoke to all of the big players in logistics and delivery and so on and so forth. But again, through the automotive supply chain, I found a company called GTEM, and they were just absolute miracle workers. This is the one company that we'd never had any dealings with before, got a really good feel for them, and they were the only ones that didn't say, oh, we'll provide you a quote for how to send all of these devices out to the NHS. The reason this came about is because do you remember when they did the Nightingales? We managed to get through to, I can't remember exactly his name, Major General, who'd been looking after that. And the advice we got was, go and do your own thing. Don't go near the official supply routes because it's just so chock-a-block and it's going to take so long. Go and do your own thing. Get them directly to the hospitals. So this is where GTEM came along to help us. Their background is, if you take a car, take the outer bodywork off, that chassis underneath, all the beautiful pressed metalwork, that's their core business. That's what they produce. So we set to with them to help us with the logistics. I think. So
it was a kind of multifaceted problem that we asked of them. So one piece was that every day we would get an email from the NHS saying where across the whole of the UK they needed devices the next day. So GTEM committed to next day delivery of kits basically anywhere across the UK. But of course, as we mentioned, one piece of that puzzle was pre-assembling all of the breathing circuits and packaging them, which meant that they needed dedicated clean room facilities at their warehouse that were approved by the IMechE. So we set up clean room facilities. And that's what you can see here. So they would assemble all the circuits, package them, and send them out. So these are some of the boxes, as you can see, lots of the packing and distribution.
Yeah, just to give you an idea, there's about 700, 750 boxes in that view. So our little workshop in King's Cross was never going to quite fit them all in.
Even without students in it. Right, so we've kind of talked a lot about what we did now, and we're going to just move on and tell you about the impact. But quickly, just to kind of summarise the timescales, we got together 17th of March. The day later, Mercedes turned up within 100 hours. We had the first prototypes back in the hospital for testing. Within 10 days of the first meeting, we had regulatory approval, and within 1 month, we had completed an order for 10,000 devices from the Department of Health that had been going out to the NHS.
So let's tell you a little bit about the impact beyond just the UK.
Brilliant. So Obviously, the whole point of all of this work was to help save lives, and that's what we were really very committed to contributing to. So where did we get to? So in the end, and these devices are still available and out in the NHS, so over 130 NHS hospitals received these devices to augment their existing supplies. There was daily distribution, so it said we'd get daily emails and requests, and they went out across England, devolved nations, and overseas territories. And we talked a lot at the beginning about this kind of controversy about CPAP versus mechanical ventilation. Over the course of that first wave, there was a really significant reduction in the use of mechanical ventilation as much more data became available about patient outcomes and risk of spread. So if you looked up to the end of August in 2020, around 54% of patients that were admitted were mechanically ventilated. If you look after September, it was about 26%. So there was a real significant drop-off in the use of mechanical ventilation, and that gap was filled by the use of non-invasive or CPAP. And if you look at various pieces of data, which obviously have now been reported, but this is one of them, if you looked at 28-day in-hospital mortality, that reduced by about 20% over that period. Now, of course, that's a multifaceted question, but I think it's fair to say that this change in the treatment pathway certainly contributed to that. So UCLH was kind of one of the figureheads for implementing CPAP right at the beginning, as you can imagine from the story that we've told. But as the kind of communication of the role of CPAP was spread, we were really, one of the highlights of this whole thing was actually being in contact with hospitals across the country as they set up their CPAP units, and we were able to communicate with them about the findings locally, about what our devices did and why, etc. So this is just one example. Many were reported. And then ultimately there was a randomized controlled trial as part of the recovery program that looked into respiratory support. And this compared basically face mask oxygen versus CPAP, and if there was a reduction in the use of mechanical ventilation by 19% and a reduction in mortality of 13% if you use CPAP compared to using face mask oxygen alone. And that data is actually still relatively recent. Finally, did it make a difference? I'm very conscious of time, so we're going to rattle through some of this now, but this kind of really just re-emphasises what I just said. So ICNARC is the kind of national intensive care audit data. I'll just highlight this figure at the bottom. So this is basically up to the beginning of September in that first year, and since then, and you can see this really significant reduction in the use of advanced respiratory support, which is mechanical ventilation, and this is for equally sick patients. So at the same time, you get a reduction in mortality and a reduction in length of stay in intensive care.
Okay, so we'll just quickly whiz through the international work, because not only did we make the devices for the UK, we also released all of the designs open source so that anybody around the world could download them to do local manufacture.
So when we set out on this programme of work, if you like, obviously we were motivated by the immediate problem, which was the NHS. But the project received a lot of media attention in the end, and we started getting contacted by loads of countries across the world who obviously, for exactly the same reasons as the UK, needed their supplies of non-invasive ventilators augmented. We had no experience of working in the kind of global medical devices world at all, but at that time, over 80 countries internationally had imposed export restrictions. So that meant there were a lot of countries either that didn't manufacture medical devices themselves, or, for example, lower middle-income countries that were left extremely vulnerable. I think we could talk for hours about what we've learned from this work, but here are some really important points. One size fits all just doesn't work. So just because we understand what it's like delivering CPAP in a sophisticated hospital in London doesn't mean we know much about what's needed if you're going to use one of these devices in a rural region in Africa, for example. So it's really important to understand the local environment if you're going to develop a medical device and the local healthcare need. Equity and trust are so important. So we went into this obviously with no expectation of making any money and with the attitude that we were going to release all of our data. That meant that we could build relationships really quickly with people in other countries because they trusted us. We weren't doing it for any reason other than to help. And it goes without saying, patient safety, efficacy standards are paramount. Our global regulatory environment is really fragmented, and that became a real challenge. So the MHRA is viewed extremely highly internationally, which is fantastic, but there's no international regulator. So how you navigate that on a country-by-country basis was extremely challenging. And I mean, that leads to my final question, which I'll leave open, but who decides how to do this globally? We learned very quickly that there wasn't really a mechanism to do this globally. And I'm not really convinced that if all of this happened again, we would be in a different position. So what did we do? First of all, we took a two-pronged approach. First of all, we released all of our designs and manufacturing instructions for free, so we didn't protect any of the IP. We did a complete open source release of all of our data. And that was so that we could support local manufacturing hubs being established in other countries. And then we also sought to work with charities and governments to donate devices to countries in need. So it was a kind of dual-pronged approach to support local manufacturing country, and where that wouldn't be fast enough to supply devices directly if we could. So these stats really just summarize where we got to. So there were over 2,000 approved requests for the free designs and manufacturing instructions, and that was across 105 countries. Despite that, there were a much smaller number of countries that actually managed to go the full path from scratch, design, manufacture, regulatory approval, and in-hospital use. But the devices are now being used in hospitals in 29 countries across the world. Over 24,000 devices have been made in local manufacturing hubs, and over 3,000 of the devices that we made in the UK have been donated out. This just gives you a flavour for some of the countries that we've worked with. We can't go into detail, we haven't got enough time, but it's been an utter highlight and privilege to work with just the most incredible teams in countries across the globe, and people that we would never have been connected to had we not done this work. This gives you a flavour of some of them. We had a real focus on low middle income countries, and some real success stories in some of those instances, and we've learned a lot from the process. So here you can see various different examples of local manufacture, use on patients, and deployment.
And again, the way we did that was full transparency. So we published everything from our testing data, all of our manufacturing data. Mercedes shared all of their tooling lists, all of their manufacturing kit, you name it. So bill of materials, the assembly procedures, everything that they needed. And then not only that, what we learned as well is we take it very much for granted. Do you want to go on to the next one? Very much for granted the equipment that we have at our disposal. Other countries just don't have that luxury. So what we found was a lot of the time they could make some of the components, but some of the sort of the needle valves and things like that, we would then help with supply. So there's a lot of pride in them being able to manufacture locally, and of course then it brings in a lot of enthusiasm to do that. We take for granted simple things like some of the O-rings. I think some of them were a little bit sort of motorsport specification, shall we say. So we helped, some of the sizes that we take for granted, it's not as easy to get those all around the world, even though they are a standard. So we helped. So that's what we did. We helped with the local assembly. They did as much of the manufacture as they could, and then the hard-to-source items or the very difficult to manufacture, we helped with the supply of those.
So we're going to close by just giving you a few examples of the ones that we made real progress with, but for kind of transparency, there were a lot of scenarios where it was really, really hard. So, we've learned a lot, and there's a lot of barriers that we still face. So it's not all kind of rosy. We solved lots of problems. This is Peru. So Peru were an incredible team of engineers who were Formula One fans, so picked up the project through the Formula One media, downloaded the designs. We also ended up working with some of the clinicians in the hospitals in Lima, so they did clinical evaluations of the devices. And in the end, the devices, so the replicas of the Venturas that were made locally in Peru, went out to about 90 hospitals, covering some of the cities like Lima, but also rural hospitals in the mountains, essentially, in Peru. And it was amazing. So we worked very closely with the embassy in particular, who did various fundraising rounds to so that we could supply needles and things into them. And this is a kind of collaboration that's ongoing. So another example of a new relationship that we've built is through the International Medical Education Trust, which is quite a small but highly impactful charity that does a lot of work around medical aid, medical education and supply, in particular in Asia. So this is one example in Palestine. So they essentially bought on a non-profit cost basis 40 devices that were delivered across 5 Palestinian hospitals. We then put in place a clinical training program, so the clinicians in the UK, and we did webinars basically where we did training so that they knew how to use the devices. And this is a kind of ongoing piece of work, also in collaboration with Medical Aid for Palestinians. And then the same charity, IMechE, essentially fundraised to build a hospital in Uganda some years ago, and we've supplied devices that eventually have enabled them to set up their first intensive care unit. Again, this is very much a program of work that's ongoing, and the most incredible clinicians, people, teams locally there who have made a massive difference to outcomes for patients there. So they're being used to treat COVID patients, but also non-COVID patients. And then finally, we did a lot of work and a lot of lobbying to try and encourage devices to be donated overseas. It became very clear quite quickly that the 10,000 that we'd manufactured weren't all going to be needed in the NHS. So it seemed natural to then send them out to other areas of the world where there was dire need. I didn't succeed at encouraging the government to do that for quite a long time until India came under real threat in last year. I forget when it was, it all blends a bit. But at this point, the government donated 1,000 of our devices out to India. You can see them going off here from Bryce Norton. And that kind of shifted things. So that set a precedent. So 1,000 went out to India, and after that, we managed to get devices donated into Nepal and various countries in Africa as well. So I'm really pleased that we made progress on this in the end, but again, many lessons learned.
There we go. We really were just the focal point for literally thousands of people working on this project. If you're really eagle-eyed, you'll see that Mercedes-AMG 8 World Championships. Earlier slides, it said 6, the pace of everything happening. So over the couple of years that we've been doing this project. But amazing support from everybody. In particular, it's worth singling out in surgical as well. They helped so much with all of the breathing circuits and so on and so forth. So yeah, so many people that came together to make this successful. And it's not the end of the story, but it's the end of the presentation. Maybe we'll come back sometime to explain what's been happening since. So thanks everyone for listening. Thank you very much. That was just one on time.
Do you guys want to stay there?
Yeah, should we stay?
Do you want to sit?
We'll stay here. Do you want to stay?
You can choose. You can stay where you are.
All right, yes, Tim wants to stay. That's fine.
Do you want to sit?
He's not wearing heels, so it's all right.
Go and sit. Go on, let's go.
Right. Well, what a wonderful, wonderful success story. We're running quite tight on time, but I do want to sort of permit some questions to be asked. We've actually got the opportunity also to ask questions online as well. So for those people who are actually online and want to ask a question, then we'll give you an opportunity to do that as well shortly. But maybe to throw it open here to the audience physically in Birdcage Walk, I think at the back in the centre. Ben, did you want to ask your question?
Yeah, thank you for that. That's absolutely fascinating. It's one thing to live through the start of the pandemic, but for you guys to have basically got involved that quickly and got stuff out the door that quickly is absolutely incredible, so well done. The number of cases we've seen in the UK, the number of cases seen worldwide, obviously 10,000 units is quite a small number, so it's almost certainly my ignorance, but are these things reusable even the masks and things, the whole setup, is that a reusable, sterilisable product, effectively?
Yeah, good point. So that's one of the things in this country. It's all about single-use plastic, and the supply chain did open up so that they could, keep using single-use. That's one of the things. Certainly, looking forward in terms of sustainability, that certainly has to change. The device itself, all the bits of hardware, they could just be cleaned and reused. But a lot of the groups that we helped with around the world, we would send the patient circuits, and then they were finding their own ways of sterilising them so they could just be reused. So again, lessons that could be learned there.
We did ultimately do some sterilisation work to characterise different methods of sterilisation. Obviously, it's quite complex. So there's the infection control piece, but also whether you erode the kind of underlying materials. So it's a challenge.
Any further questions? Yes, here at, well, we'll take the one at the front on the left, and then we'll switch back to Nikki at the back.
Hi there, fantastic presentation. You talked about what you got as a basic input, which was a piece of technology which was pretty simple, had existed 10 years ago. Do we overcomplicate many other things today? Because I think what you're going to say is yes. Because I certainly believe that there are many opportunities where we make things far too complicated because we can, rather than because we should. So I'd be interested to know if you think that's happening across engineering everywhere.
Do you want to go?
You go, and then I'll go. Yeah.
I'm anticipating what Tim's going to say, but yeah, I think we completely agree with you. So one of the things that you really learn when you go into the hospital is how kit's used, and actually it's rarely fully characterised kind of in a local setting, and there's often quite a lot of fancy bells and whistles that are making up for quite poor engineering or overcomplicated engineering, but it's almost kind of reassuringly expensive. So I think there's a real challenge.
Walking into it as an engineer, I found it very frustrating. I've called it Goldilocks engineering, because you go and say, what's the flow rate for? Oh, it can't be too high, it can't be too low, it's got to be just right. Okay, what's the pressure then? Same deal. Can't be too high, can't be too low, it's got to be just right, which is no good. We've got to design something for you to solve a problem. Another really nice example, do you remember the electronic manometer that we did? So we were doing some testing on that, and the idea was, well, let's characterise it against a known piece of kit. So we went and got one of the really expensive pieces of equipment in the hospital to back it against. And what we wanted to see was, we were worried about our device and how much fluctuation we were getting and how much is acceptable. Idea is, if we get the fluctuation within the state-of-the-art piece of kit, then that's going to be acceptable for getting it through approval. We plugged in the state-of-the-art, and this thing's going like this. And so, of course, they've never seen the raw signal, and they're going, well, we've got patients on these things. Is this what they're seeing? So yeah, it's very, very interesting to see that sort of thing going on.
I think also, when you talk to people who are actually treating patients, the bits of kit that they really need are often really simple. They're not massively sophisticated solutions. You can have a lot of impact very quickly with really, really simple, kind of what we would consider low-tech innovations.
Great, thanks very much. We've got one online question, but I will take the question first from Nikki at the back left. Yeah.
Hey, thank you very much. So you kind of alluded to it earlier in the presentation, but you've developed this entire process for going from nothing to spinning up very quickly to engage with a new threat. And you alluded to the fact that do you think the world has learned from that? And do you think, faced with something similar or a global threat, do you think the world has learned from that? Or do you think we'd be back to square one all over again? Or has this shown that something different can be done?
It's an obvious answer, isn't it?
Yeah, it would be flippant to say that nothing's been learned, because obviously a lot has been learned. But I think a lot of the reasons why we could make progress really quickly were because of, transparency, because bureaucracy was kind of just cut through, and there was an openness of communication and an urgent need. In all honesty, especially in terms of the global context, I'm not really convinced that if it all happened again, the world would work any better together to fix the problem. one of the biggest challenges for us, having done the UK piece, for example, was then going to some of the big international organisations and saying, well, we can make another 10,000. Can you help them get them out there? We could make 100,000. HPP would have just kept going. And that was just incredibly difficult to navigate. So it's not, and everything that we did internationally, we've done on an ad hoc basis ourselves, working with individual countries and local manufacturing hubs, which just can't be the most efficient or pragmatic or scalable way of responding to a crisis. So it's not immediately clear to me that would be fixed another time.
And the fact that we were doing it not for profit really helped to get the message across and get things out there. If you could do it for free, then that would be another story, and it would, then the possibilities really would increase. But unfortunately, it always comes down to somebody's got to pay for it. And despite
who should that be?
Global pandemics, people still don't seem that keen to actually pay for it.
Good. We've got 2 online questions now, which we're going to take through Alice, and then I will throw it open for a final question from the floor. And given the time, I think then we will need to close. But Alice, did you want to pick up the 2 questions online?
I mean, I have to say, a lot of the comments coming in are just, wow, this is amazing. Your work is really inspiring, particularly the speed and the size of the rollout. I think your slide where you effectively show a month and all that was achieved, and I was reflecting here, I think most of us in the room perhaps, the most we were contributing was pointing out that people were on mute.
Well, we did that too.
But the 2 specific questions, following on from the conversation just now. From an idea, could you describe the funding commitments that you were able to achieve?
The funding?
Funding commitments that you were able to achieve. And the second question, which isn't linked, but could be, are you proposing to offer this presentation to TV?
Shall I go first on funding, or do you want to?
You can tell how it came about, yeah.
Yeah, I mean, so, there were various pieces of the puzzle that aligned. So, we started off, we didn't have any funding. And, the priority was the ventilator challenge. That was the focus of the national effort and funding at the time. So we were outside the ventilator challenge. And we were lucky. So basically Mercedes were happy to do it at no cost in the first instance, which was brilliant. UCL also just put up money. So I think we rang our faculty manager one Friday afternoon and we're like, we're going to need 200k by Monday to do X, Y, and Z. And I mean, if any of you don't work in universities, which I'm sure you don't, like that doesn't happen ever. But she managed to turn it around and rang us back in about an hour, and they'd covered that. So, we had massive backing for our institutions. And then ultimately, we kind of lobbied and got the government support. But there was a lot of tension around how that aligned with the ventilator challenge at the time.
It's quite nice how that came about, isn't it, about the funding? It was an online call, and it's like, so how many do you think you can make? Okay, so we've got this many hospitals. How much do you reckon it's going to cost for each kit? All right, so if we give you an order for £20 million, we'll give you a ceiling of £20 million, do you reckon that will cover it? Okay, we'll do that. So that was originally for the Ventura and the oxygen analyzers. And then behind that, we delivered, the hoods and the pressure monitor, all of the patient circuits, all of the logistics that we set up, and we gave them £4 million back. Yeah. In simple terms.
Good. I'm going to offer it for one last question, and it will have to be one last question. I think, Mahendra, you had your hand up first, so you were the quickest, so go for it.
And first of all, thank you for the wonderful presentation and the wonderful job you did. And my question goes on into the area of the regulatory framework. What are the struggles you had when you want to take out this product to the other 28 countries into the local manufacturing units? And what was the support and the response of the local regulatory bodies in those countries?
a really good question. So I said, the IMechE array are held in really high regard internationally, which put us a really good standpoint. And the IMechE array also had a very open approach. So members of the IMechE array were very happy to talk to regulators in other countries. So they were very open in their collaborative kind of commitment there. There's no short answer in essence. So we experienced a whole range of scenarios from countries that don't have a medical regulator through to countries which do but have never manufactured devices locally before. So Paraguay is one example. So these are the first medical devices that have ever been made in Paraguay as opposed to imported. Through to, I'd say one of the kind of best practice scenarios was South Africa. So the regulator in South Africa did a back-to-back approval based on the IMechE array approval that really expedited that. And actually Mercedes ended up donating 1,000 extra devices into South Africa. So there's no quick answer. We've learned a lot, but it has really highlighted that there is not that international standard, and it's a very fragmented global situation, which I think is part of the reason why, if we went through all of this again, there's still massive barriers to how you roll out medical devices in this kind of situation.
Becky, Tim, thanks so much for coming this evening and sharing your really sort of inspirational success story. So can we show our appreciation again? So, thank you for attending this evening. For those of you who are leaving now, I wish you a safe travel home. And sorry, yes, I have forgotten Peter. My apologies. To express a vote of thanks to the speakers this evening. So.
Right. Well, sorry, self-organised.
Yeah. Thank you.
Well. Becky and Tim, huge thanks, both for the lecture itself and, more importantly, the work that you've described and have undertaken. I did actually visit your IMechE space, I think as it's called, in King's Cross last year, as part of the design challenge. But I hadn't realised what was going on, and I obviously missed an opportunity, or maybe you'd sent everything away by that point. I think it was June, I think, last year. I mean, we've not had a lecture for several years now. So a trite comment would be to say, well, this is the best lecture I've heard for several years. But in reality, it is actually one of the best lectures I've ever heard. And I say that, quite sincerely. It was polished. I felt it was very relaxed, and it told a story, an extremely inspirational story at that. And even just preparing the presentation that's quite demanding. I can say that because I'm doing one myself, and I'm now quite worried whether I'll be able to sort of match the standard of what you've done. The technical content was very interesting. I was actually also extremely interested in the sort of process side of things. And the thing that stuck in my mind was this 2-minute window that you had from number 10 Downing Street for a yes or no decision. It's a bit sort of black and white, that, isn't it? I mean, it went the right way. But I can think back to probably tens, if not hundreds, of situations in my own sort of working life where a 2-minute decision would have been quite helpful, even if it was the wrong one. But also I think what this illustrates is that I think healthcare engineering is an aspect of our work, of the work of engineers, which is a bit underappreciated. We tend to think a lot, at least in our institution, of cars and trains and aeroplanes and things like that, without realizing what's going on in the world of medical care. And in fact, one of the things I found last year particularly when I was talking to young people, was to illustrate this point and to point out, for example, in the case of COVID, how the world had responded in producing COVID vaccines. And I was keeping a sort of running commentary on how many vaccines had been produced, as Alice may remember, by that particular point in time. And by the way, today's figure is 12.7 billion. So that's from the beginning of last year, I think, the world and its manufacturing engineers have produced almost 13 billion. That number rings a bell. Is that the number of years the universe is old? Something of that order. Anyway, just the final point, and I apologise to those who are in the council meeting today. We obviously had the very sad situation with the loss of our Queen. But I did come across a very nice little quote from her, which said, at its heart, engineering is about using science to find creative, practical solutions. It is a noble profession. And I think your work illustrates that amply. So thank you very much indeed. We have a small gift for you here, each. So there we are. Perhaps you could show your appreciation again.
Many thanks, Peter, and I think at that point we'll close.